Well, let's do the second. No, let's do the first derivative. Low. Yeah, thank you. Come on, focus, focus, focus. What is the derivative? Minus high. D low. All over. All over low square. Come on, come on. So this just turns into 0. 0 minus 6 times 2x, that's negative 12x. So f prime of x is negative 12x over x squared plus 3 squared.
Okay, got that.
Okay. To determine the concavity of a polynomial, we need the second derivative. So that's the derivative of the first derivative. F double prime. This one might have gotten a little funky.
Okay, got very funky.
Resume it.
132x squared plus 4x.
So, low times d high, which is what? Come on, guys.
Which is
Minus
negative 12x.
high.
D low is
Now d low is 2,
quantity x squared plus 3.
but now we have a chain rule.
4x.
What's the derivative?
4x. No, times 2x.
So it should be times 2x.
That's what I meant.
Okay. All over x squared plus 3
To the 4th.
to the 4th power.
Things get messy.
Now what do you suggest?
Because my calculator is possessed.
Simplify the numerator.
Confirm that.
You guys aren't terribly focused. Come on.
Negative 12 times
Let's-
quantity x squared plus 3x.
Multiply this here. We're going to get, that's a plus. 12 times 2 is 24. 24 times 2 is 48. So negative 12 times x squared plus 3 squared plus 48. 48 what? 48x squared times x squared plus 3 all over x squared plus 3 to the 4th. What do you suggest we do now? What is it we're trying to do here? What was the point of the problem?
Is to find the positives and negatives of the second derivative.
We need to find the positives and negatives of the second derivative. That may mean that we don't necessarily have to simplify all of it. If you guys need to listen carefully. If the question had just been find the second derivative, then yeah, we would want to simplify this as far as we can. But all we need to do is find the positive and negative regions of the second derivative. We may not have to simplify it as far as it needs to. You understand what I'm saying?
Yeah.
If you continue to simplify this, you may just be doing a little bit of unnecessary work. Okay? So, just saying, don't do more than you really need to. From the numerator. Okay. Thank you. So what can we factor out of the entire numerator? It may help to simplify this a little bit more before we start trying to do the second derivative thing.
Wait, is this just the first derivative?
This is the second derivative.
That is the second derivative?
We're going to simplify a little bit, but this is the second derivative.
Okay, I was scared.
What can we factor out here?
X squared.
We can factor out a negative 12 x squared plus 3 maybe. What's that going to leave? 1 x squared plus 3 minus
3. No.
4 x squared. Now, do we really need this 1 parenthesis x squared plus 3?
No.
No. So that just changes into negative 3x squared plus 3. And that's all over x squared plus 3 to the 4.
Now we need to find critical values, right?
We're not quite done yet.
Is it critical?
It is critical.
What was the point of taking out this x squared plus 3? You can cancel with one of these down here, right?
Oh, yes.
One of these x squared plus 3's can cancel with one of those. So now we have negative 12. Quantity negative 3x squared plus 3 over x squared plus 3 cubed. So that's a simplified form there of the second derivative. And even to make this a little nicer, isn't there something else we can do here? Can we take out a negative 3?
We could.
So if we make that 36, if I take out a 3 here, doesn't that, or a negative 3, doesn't that make that a positive 36?
Oh, yes.
And now we're left with x squared. Careful, I'm taking out a negative 3, so it'd be minus 1. Now we're ready to take a look at some critical values. Critical values of the second derivative, in this case, are going to be what makes the numerator 0 or what makes the denominator undefined. Let's take a look at the denominator. X squared plus 3
Never be
to the third, never going to be 0, because x squared plus 3 is always positive. Always positive. And then if you raise that to the third power, that's always positive. So we're not going to get any critical numbers from this denominator here, but the numerator,
We could definitely get one from there.
we'll actually get 2.
Yeah. At least one.
X squared minus 1 changes into x minus 1 times x plus 1. So we have a negative 1. We have a positive 1. Now we're trying to figure out the concavity, so we're going to choose test numbers and plug it into the second derivative to test where the second derivative is either above 0 or below 0.
-2.
So let's test negative 2, let's test 0, and let's test
4
positive 2.
-1. 3.
Yep.
108.
Now, didn't we say that the denominator is always going to be positive? Always. So that's always just going to be a plus sign, the denominator. But if you plug in a negative 2 into the second derivative, you're going to get a negative 2 minus 1, which is a negative, a negative 2 plus 1, which is a negative. Negative times a negative is positive. So that's a big old fat positive region right there when x is less than negative 1. Now when we're testing 0, we're going to get a positive on the denominator again.
I don't know.
A negative in the numerator. So that's a negative region. There might be a time where it goes like positive, positive, negative, or negative, negative, positive. Yeah.
So glad.
We're gonna overcome it 2 points.
So glad I didn't do it.
Okay. Shh. What about a positive 2? Come on.
It's positive.
It's a positive over a positive. So we
It's
get
a positive.
positive.
Positive, negative, positive.
Okay. So now we have to
We have to draw conclusions.
determine what this means. This graph is concave up.
Ah. Excitement building.
Concave up over which intervals?
Negative infinity to negative 2.
Negative infinity
Never mind.
To negative 2.
to negative 1. Negative 1 was that critical number there. So it's negative infinity to negative 1. It's also concave up from 1 to infinity. It'd be concave down over the interval negative 1 to 1.
Oh, those are exciting equations.
That
I really love that, Mr. Up.
was a crazy graph.
Whoa, show us what the graph looks like.
Let me show you the graph.
Just know it's something Zane was trying to convince me. I never would have done it. I never would have. I never would have done it.
Oh my god.
Never would have done it. Zane was just trying to Oh, I hate myself right now. Thanks for that.
Check out the graph, you guys.
But I would.
Yo,
Hey, dude,
Sorry.
graphing stuff. Doing that.
this is negative 1 right here. This is positive 1 right here. Between negative 1 and positive 1, the graph is kind of turned down, right?
Mm-hmm.
Didn't we say it was concave down between negative 1 and 1?
Mm-hmm.
Now, from negative infinity to negative 1, it's kind of hard to tell, but you see how the graph is kind of curving upward?
Yeah.
And from 1 to infinity, it's kind of curving upward as well. Anyway, that's what the graph looks like there. Let's do another one.
Okay. Can we do this one on our own?
I hate myself right now.
Can we do this one on our own?
Sure.
Oh, sweet. Yes.
Yo. Yes. F of x squared plus 1 over x squared minus 4.
Alright. I'll do it. Any sense? Because I can't figure out anything that will make this.
Alright, let's see. The first derivative
Bottom can't be 0.
is low
Put a 2 in there, or negative 2, and it turns into 0.
d high minus high
And then there was 2 points.
d low all over low squared. Low d high minus high d low. Now what do you suggest?
Well, you're gonna combine 2x into 2x squared.
Right there?
1x squared minus 4.
Okay, so that's going to be 2x cubed minus 8x minus 2x cubed.
Plus 2x.
It's got to be minus because we got to distribute this minus sign as well. So then 2x cubed cancel. So you've got negative 10x over x squared minus 4 squared. That's the first derivative. Okay. Now the second derivative. Again, I'm noticing a lot of people that know what to do. There are just some small arithmetic mistakes happening. And you've got to know where you're making these, otherwise you're not going to be able to do better next time. You've got to be able to catch yourself. Okay? If you haven't attempted this and gotten to a certain point, if you're just watching me do everything, you're not going to get the preparation you need to do these on your own. All you're going to be ready to do is copy someone else, which isn't very good practice. Not good preparation. So, low times d high minus high
all over x squared minus 4 squared squared, which is x.
Okay? So let's simplify here.
So if you combine all of everything,
So this is negative 10 times x squared minus 4 squared. Now what? Plus 40x squared.
x squared minus 4. Hold on, negative 10 x squared.
So now you can take out a negative 10 x squared minus 4. X squared minus 4 minus 4x squared. Now hold on a second, I think this is where I can see a lot of mistakes happening right at this point. You need to understand where this all came from. Where did this come from? The 40x squared, I took out a negative 10. That's why the negative 40, or the 40 turned into a negative 4. And then I took out the x squared right here. And this is all over x squared minus 4 to the 4th. Now, x squared minus 4 minus 4x squared. That's negative 3x squared minus 4. X squared minus 4 crosses out with one of those. And then I'm going to factor out a negative 1 from here, making that turn into a positive 10. So it's positive 10 times 3x squared plus 4 all over x squared minus 4 cubed. Okay. That's the second derivative, which I know it's a bit of a struggle because there's a lot of arithmetic and algebra involved, but we need to be getting to the point where we can get to this not easily but accurately. I'm not saying this is ever going to be easy necessarily, but it should become a lot more accurate. If not, you need more practice, okay? And not just what we're doing in class, going home and doing the homework, making sure you're checking your answers. Are the answers correct? That sort of thing. Okay? Because I took out a negative 1 from right here. Okay? We need to do a new definition here, kind of in the middle of this problem. Points of inflection. Write this down, that phrase, points of inflection. Because we need to make sure that we're using accurate math terminology. A critical number is where the first derivative equals 0, or where it's the first derivative is undefined. So we're not finding critical numbers anymore because we're with the second derivative. You guys follow? What do critical numbers have to do with? Critical numbers are where the first derivative is equal to 0, or where it's undefined. You follow?
Yeah.
Points of inflection are found when the second derivative no, that's only with the first derivative is 0 or undefined. So at this point, we're going to set this second derivative equal to 0, but it's not because we're trying to find critical numbers. What are we trying to find? Points of inflection. You need to also write this. They're found when the second derivative is 0 or undefined. They occur when the graph changes concavity. That's when you have a point of inflection. When the graph switches from concave up to concave down, that's a point of inflection. For example, this is not part of the example we're on. This is just a little side note here. Draw this little graph right here. You got it? This part of the graph right here, would you call that concave up or concave down?
Upwards.
Is it a smiley face or a frowny face?
It's a smiley
So
face.
that's concave up. This is concave up. Okay? This part of the graph right here, that's concave down. So, you guys, right here, where it switches from concave up to concave down, what do we call that? That's an inflection point right there. That's an inflection point or a point of inflection, but a point of inflection occurs when the graph switches from concave up to concave down, or concave down to concave up. When it switches concavity, you have a point of inflection. When do they occur? It's when the second derivative is equal to 0, or when it's undefined. Okay? Be careful. So, let's get back now to our example. We've got the second derivative right here. When's it going to equal 0? When is it undefined? First of all, you need to really think hard about this right here. 3x squared plus 4. It doesn't factor.
Is 3x squared plus 4 ever going to equal 0? Just think about the term 3x squared. Whatever x is, what is 3x squared going to be? Positive. And then you add 4? Positive. And then you times 10? Positive. Positive.
Wait.
That whole entire numerator, 3x squared plus 4 times 10? It's never going to equal 0.
No.
Hey, Brady, who am I? Solved it.
Okay. You guys are starting to lose it. This is never going to equal 0. So we don't have any points of inflection that come from the numerator, but this right here, that could equal 0 at positive or negative 2. Yeah? think this class needs a good old-fashioned dose of seating chart.
No.
It really does sound like it.
Mr.
It's really easy to do. It takes me about 5 minutes. Should we try it?
No, Mr. Huff, stop.
Because I'm about this close to a good old-fashioned seating chart for the rest of the year.
I'd like to sing it now.
Okay. Can we change our ways here?
Yes, we can, Mr. Huff.
Okay. It's a short day. We got a lot to get through here.
You're right.
And you guys are slowing us down.
You're right.
Okay. So, we have a -2 and a +2. True or false? These are going to be inflection points.
Yes, sure. It is true.
You said 0 undefined, or is it just 0?
0 or undefined.
So when is it being inflection? Or because it's undefined?
So it's true.
So it is true. So it's an exception
Remember, an inflection point occurs if it changes concavity. What if these are all plus, plus, plus?
to, well, then there's no,
Then it didn't change concavity, right?
so it's,
You understand what I mean?
yeah.
So in this case, would those be points of inflection? No.
So only if there's concavity can it be a point of inflection, because 0 is undefined.
That's where the possible points of inflection are.
Possible, so we don't even know yet.
And then if they change concavity, then they are points of inflection. So, let's test some test numbers here. We're going to do -3, 0, and +3. Didn't we already say the numerator is always positive regardless? Numerator is always positive. Doesn't matter what x is. Now, if x is -3 in the denominator, -3 squared, 9. 9 minus 4 is 5 cubed. That's positive. So have a positive region there. If x is 0,
And negative,
then we have 0 squared minus 4 cubed. -4 cubed is negative. So it's a negative region right there. And if 3 is +3, 3 squared is 9 minus 4 is 5 cubed is +125.
So these points are points of inflection.
These are points of inflection because they change concavity. So the graph would be concave up on the intervals -∞ to -2 and from 2 to infinity. And be concave down over the interval -2 to 2. Now, this is also something you guys might have to be prepared for on your homework and possibly even the exam. Okay? You might have to go back and actually show on the graph that what you've come up with is accurate. So let's just go back and graph this. The original function there. Okay?
Well, it's got vertical asymptotes at 2 and negative.
To show that you're going through the whole, if this were an AP test question, they'd want you to go through the whole thing stuff. So,
Vertical asymptotes at 2 and negative.
we have vertical asymptotes at 2 and -2. This is pre-calc stuff from last year, you guys. Vertical asymptotes occur when you have undefined values. X can't be 2 or -2.
There's a horizontal asymptote.
We have a horizontal asymptote when you divide the leading coefficients. 1 divided by 1.
It's 1.
So we have a horizontal asymptote at 1. I know I'm going through this pretty quick, but this is pre-calc stuff. Now, x-intercepts occur when this equals 0. Is this ever going to equal 0?
No.
X squared plus 1 is always positive, so there are no x-intercepts. Y-intercepts occur when x equals 0. If x equals 0, those are gone. You just have 1 divided by -4. That's -1/4. So you have a y-intercept at -1/4. Do you have an idea what these graphs even are supposed to look like, these rational functions? Remember there's a piece here, maybe a piece down here. You remember how there's pieces everywhere? A lot of times you can just fit in the pieces just thinking about it. You see where my pen is circling? You're either going to have a piece of the graph here or down here. Those are your two options.
That's fine.
But is there an x-intercept right here or anywhere over here?
No.
So can the graph have a piece like this?
No.
Because it's not going to cross x-axis.
It's not.
So the graph has to have a piece right up here in this corner. You can use the same argument over here on this side. Is there an x-intercept over here?
Nope.
So the graph can't be down in this portion. It's got to be up in that portion. Okay? This piece of the graph has to look like that. There aren't any x-intercepts to allow the graph to pass up through the x-axis up in here. So, just looking at the graph.
Concave up or concave down right here? What do you think? That's smiley face or frowny face?
Up.
It's concave up. Isn't that what we said as our answer? -2 to infinity, or negative infinity to -2?
Yep.
And then between -2 and 2? Concave down, and from 2 to infinity?
Concave up.
It's concave up.
That's what I got. See?
So that's what the graph would look like.
Let's talk about a second derivative test, then we're done.
You know what I did wrong? When I factored out the -10, it didn't change the sign.
Is that what it was?
It's fatal to my
Okay.
solution.
Here's the second derivative test. Let f be a function.
Second derivative test.
What's that? We kind of did already. We went over the first derivative test, and we talked about the second derivative test, but we never wrote it down. Let f be a function such that f prime of c is equal to 0, and f double prime exists on an open interval containing C. Now we talked about this last time. We didn't write it down. All the second derivative test is another way of finding extrema. The first derivative test is a way of finding extrema. The second derivative test is a way of finding extrema. What is this right here? F prime of C is equal to 0.
It is an extrema.
If the first derivative is equal to 0, is that a critical number or an inflection point?
It's a critical number.
So that's a critical number.
If f prime of C is equal to 0, that's a critical number, or a critical value. What generally occurs at critical values?
Extrema.
Extreme. So what this is saying is that f double prime exists on an open interval containing C. So your critical value is inside the interval that contains this second derivative. So think about this. If you have a graph that's concave up and your critical value is in that interval, what does that mean? If you have a graph that for some interval is concave up and you know there's a critical value in that interval. Let's draw this out. Let's say that the graph is concave up and you know you have a relative extreme in that interval. What kind of extreme does it have to be if the graph is concave upward? It's got to be a minimum because the graph is concave up. You follow?
Yep.
If the graph over some interval happens to be concave down over, and you know there's a critical number in that interval, then what kind of extreme does it have to be? it has to be a maximum. Okay? That's what the second derivative test says. First part of it is if f double prime of c is greater than 0, then f has a relative minimum at C. This is where you got to keep this straight.
What does it mean for the second derivative to be greater than 0? If the second derivative is greater than 0, that's concave up or concave down? It's concave up, right? But if it is concave up, that means the extreme has to be a minimum. You got to keep this straight. If the second derivative is greater than 0 at that point, it's a minimum. Because a concave upward graph
has a lowest point. Over here, if f double prime of C is less than 0, then f has a max, relative max, at C. There are some cases where the second derivative test fails because the value of C happens to be a number that's undefined, and if it is undefined, you couldn't plug it into the second derivative. Does that make sense? So then you'd have to revert back to the first derivative test to find the extreme. So this will probably be our last example, and we're going to use second derivative test. Ooh, this one's an easy one. All right, good. Use the second derivative test to find what? What are we even finding? If I tell you we're going to use the second derivative test, does that mean we're finding concavity or extremely? Extremely. Okay. And we're finding extremely using the second derivative. Okay. And also using concavity in a way. But we're only using concavity to find extreme. Yeah. Okay. Let's take a look at the function. Negative 3 x to the 5th plus 5x to the 3rd. Now before you just start plugging away, let's make sure that you're plugging away in the right direction. Write down these steps, you guys. Find the first derivative. And before you just jump right into the second derivative, you need to find critical values. Because you're going to be plugging those critical values into the second derivative. So now that you have critical values, then you find the second derivative. And you plug critical values into the second derivative. So you need first derivative, then you need critical values, then you need the second derivative. Yeah.
So can you not find the critical values at the second derivative stage?
Those are inflection points.
Oh, okay.
Yeah. Alright, so f prime. This is a pretty easy one, right? Maybe?
Yeah, this one's way easy.
Negative 15x to the fourth plus 15x squared. Now, before we jump right into the second derivative, let's find the critical numbers. So that's where you set this equal to 0. And we should probably factor something out here. Negative 15. Keep going. I would factor out negative 15x squared. Because that would leave x squared minus 1.
Yes.
So the critical values are x. Yes, from here, they do equal plus or minus 1, but there's another one from right here, negative 15x squared. That equals 0 when x equals 0. So we have three critical numbers, plus minus 1 and 0. Now let's go back and find the second derivative. Now you guys, do we want to find the second derivative of the factored form or the unfactored form? I would do the unfactored form, because then you wouldn't have to do a product rule. Here, this is a simple power rule stuff here.
Well, the product rule would be very rigorous.
So going up here, we're going to get negative 60.
Thanks, Dave.
X to the third plus 30. X. Now we plug in our critical numbers. You could either do it here, or if you wanted to simplify this, I suppose you could simplify it to take out a negative 30x. Be 2x squared. So you could factor it if you wanted to. It's not super necessary. But we need to find the value of f double prime negative 1, f double prime of positive 1, and f double prime of 0. Yep.
Why don't we just, because can't you find the extrema at the first derivative doing the same exact thing?
You can find extrema using the first derivative. But this problem asked you specifically to use the second derivative
I feel
test.
like this is just kind of
It's preparing you for something big. This is all pointless until you get to stuff.
Oh,
That's
okay.
what I learned.
That's
Yeah.
what it is.
Ready.
This is just
So eventually
exercising to get you ready for application.
I'm excited that.
So
Yeah.
f double prime of negative 1.
30. Just 30.
Positive 30.
Yep.
That's what I got.
Negative 1 cubed is negative 1 times negative 60 is positive 60. And then 60 minus 30.
Oh, I know what I did.
Alright? What about f double prime of positive 1? Now hold on a second. Let's stop right here before we do 0. From here, this f double prime of negative 1 is greater than 0, right? Because 30 is greater than 0?
Yeah.
What does that mean happens at negative 1?
that interval is a concave upward interval because the second derivative is positive. So what does that mean about -1 in terms of an extreme? Minimum or a maximum? -1 is a minimum.
This means there's a minimum at x equals -1. Now this over here, f double prime of +1, that turned out to be less than 0. So that means the graph is concave down on that interval containing 1.
So if the graph is concave down, what does that mean happens at x equals 1?
There's a max. There's a max at x equals 1. Okay. Now what is f double prime of 0? If you plug in a 0 for both x's, you get 0 plus 0, which is 0. Now, you guys need to listen carefully to this. The second derivative test clearly states that f double prime either has to be greater than 0 or it has to be less than 0. It can't equal 0. Okay? So, the second derivative test fails.
It's not valid.
Okay?
The second derivative test.
So we need to go back and use the first derivative test at x equals 0.
Wow.
So the first derivative was negative 15x to the 4th. I already forgot it. Negative 16x to the 4th plus 15x squared. Remember the first derivative test, you had to do the critical numbers on a number line? Now, we just need to see what happens on either side of 0. Okay. So, we're going to test -1/2 and +1/2. And again, don't worry so much about the value, just think about the sign. Is it positive or negative? So, if you plug in -1/2, then raise it to the 4th power. That's positive. Actually, we do have to worry about a sign here in this form. Let's do the, wasn't there a factored form of this? Negative 15x squared, and then x squared to -1. Let's actually use the factored form. If I plug in -1/2 and square it, come on, positive or negative? But a positive times -15 is negative, and then -1/2 squared?
It's positive. 1/4.
It's positive 1/4, right? And 1/4 minus 1? Negative times a negative?
Positive. Always a positive.
Big old positive right there.
Amen.
Now, with positive 1/2, 1/2 squared is positive times -15, though, is negative.
Negative.
1/2 squared is 1/4. 1/4 minus 1 is negative, so that's another positive. So what does that mean?
It's not an extreme.
It's not an extreme. If it went from positive, that means it's increasing, to negative, that means now it's decreasing, so that would be a maximum. But if it's increasing and then increasing again,
It could be if this were something that were undefined, but it's okay for x equals 0. What this is, you guys,
Just we graph it and see.
what this is, just at 0, is this kind of a thing. So it switches concavity, right? At x equals 0, but is that a minimum or a maximum there? No. So hold on, we're not even done yet. X equals 0 is not an extreme. These are extremes.
So we have to test the form.
But now we got to go back and find out what the y value is. We know there's a min at -1 comma what? And we know there's a max at +1 comma what? How do we find out what those y values are? Plug them back into the original. Okay. If x equals 1, that's not that hard. If x equals 1, 1 to the 5th is 1 times negative 3, that's negative 3. 1 to the 3rd is 1. 1 times 5. So negative 3 plus 5 is 2. So when x equals 1, we have a max value of 2. What about when x equals negative 1? Negative 1 to the 5th is negative 1 times negative 3 is positive 3. Negative 1 cubed. Negative 1 times 5 is negative 5. 3 minus 5 is negative 2. So there's a min value of negative 1 comma negative 2. Woo! Right on time. That's the end.
So it's safe to say that it is symmetrical at the origin.
Probably it just makes sense.
It's symmetrical to the origin. Yeah. Yep.
Sweet.